Now, we are going to continue with the Chebyshev's inequality now. Chebyshev's inequality. And Chebyshev actually is the advisor of Markov. So Markov, the previous guy, Andrei Andreevich Markov, is the student of Chebyshev. Okay, so if you check the birth year and the death year of Chebyshev, you will realize that Chebyshev is a lot older than Markov. Markov is the student, Chebyshev is the teacher. However, after his student has developed this Markov's inequality, Chebyshev has studied further on this Markov's inequality, and he has introduced another inequality, which is going to be much more helpful for us to prove the further limit theorems. Okay, so Chebyshev says that let x be a random variable. This time we know its mean and we also know its variance. So the expected value of x is equal to mu and the variance of x is equal to sigma square. So we know these two things. But by the way, we do not know the distribution of x again. Just like in the previous inequality, we do not know its distribution, but we know that its expected value is equal to mu and its variance is equal to sigma square. Now, please be careful, my friends. Just because I am using these symbols does not mean that x is normally distributed. So sometimes some students think that because we are writing mu and sigma square here as the expected value and the variance, because we are using these Greek letters, they think that we know the distribution and the distribution is normal. No, actually it is not. I am just writing this expected value as mu and variance as sigma square just for symbolic purposes. Okay, so the random variables distribution is unknown. I don't know if it is normal or if it is exponential or uniform or distributed with any other unknown distribution. Okay, so I do not know anything about random variables distribution, but I only know its expected value and variance. And this time, x can also take the negative values as well. So we are not looking for a random variable which is necessarily non-negative. Okay, x can be any random variable. All we know about this random variable is its expectation and its variance. Now it says, for any positive real value k, the probability of the absolute value of x minus mu to be greater than or equal to k. So let us read this probability. So what does that mean? Now, at the first look, it is not very easy to understand that probability, right? So what is mu? Mu is the expected value of x. What is x minus mu? It is the difference of the random variable's value from its average value. So x minus expected value of x means its deviation, right? And since we have absolute value here, we call this difference absolute deviation. So that absolute value is called the absolute deviation. So the probability of the absolute deviation of random variable x from its mean value to be greater than or equal to k, or in other words, the value of the x to be at least k units distant than the expected value, that probability, my friend, is less than or equal to the variance of that random variable divided by the square of that k value. Okay, so it states that for a random variable to deviate from its mean more than k units, okay, the probability of a random variable to deviate from its mean more than k units has a less probability than the ratio of the variance and k square. Okay, now you are going to say, I mean, what we are doing here, this theorem or this inequality is a very, very important inequality, which is going to help us to prove the further limit theorems. Okay, so step by step, we are moving forward. The inequality developed by Markov is helpful to prove the Chebyshev's inequality, and the Chebyshev's inequality is going to be helpful for proving the further limit theorems. Now let's prove the Markov's inequality. I mean, if Chebyshev's inequality, if Chebyshev is telling the truth or not. Now the Chebyshev says that the probability the probability of the absolute deviation of a random variable from its mean to have a greater than or equal value than k, okay, is less than or equal to sigma square, the variance of that random variable, divided by k square. Now, let us look at this probability. If I take the square of the both parts, you know, this is an absolute value function. If I take the square of the both sides, the probability is not going to change. So the probability that x minus mu square to be greater than or equal to k square is the same as the probability of the absolute value of x minus mu to be greater than or equal to k, because the solution sets of these inequalities are the same. Okay, they both have the same solution set. And you know, according to the Markov's inequality, so remember what Markov's inequality says. The probability of a non-negative random variable to be greater than or equal to a is less than or equal to its expected value divided by a. So this is the Markov's inequality. Now check that out. Now, if you take the square of the both sides, x minus mu square is going to be a non-negative random variable, right? So the left-hand side, the random value on the left-hand side is going to be a non-negative random variable. And the right-hand side is just going to be a constant. And this is a tail probability, just like in the Markov's inequality. Now, according to the Markov's inequality, the probability of the random value to be greater than or equal to that constant must be less than or equal to the expected value of that random component divided by that threshold value, right? So which is basically the above is the variance of x. I mean, if you remember, this is the variance formulation, right? The classical formulation of the variance. So mu is the expected value of x, and the numerator is the variance of x, and the denominator is k square. Therefore, that probability is definitely less than or equal to sigma square over k square. So the Chebyshev, the proof of the Chebyshev's inequality is very, very, very easy when you understand the Markov's inequality. Now, we are going to use the Chebyshev's inequality in a question. So it says, remind yourselves with question 1. What was question 1? So there is a manufacturing facility which manufactures a certain product, and on a weekly basis, the average number of products that they manufacture is 50 on a weekly basis. But we do not know the distribution of the number of products that they manufacture. What we only know is the manufactured quantity or amount can only be a non-negative random variable. Okay? So this time it says, suppose that the variance of the number of items produced during a week is 25. Okay? The variance of the number of items produced during a week is 25. So we know that right now, we know that not just the expected value of the number of products produced weekly, we also know its variance. So we know two things about that random variable. The question is asking me, again, without saying anything about the probability distribution. What can be said about the probability that this week's production will be between 40 units and 60 units, boundaries excluded? So 40 and 60 is not counted. What is the probability that this week's production to be between 40 and 60, but 40 and 60 are excluded? So the question is asking me this: what is the probability of the number of units that is going to be manufactured on the next week to be between 40 and 60? And that probability, what I know about that probability is equal to 1 minus the probability of the quantity, manufactured quantity's deviation from 50 to be greater than or equal to 10, right? So this is the complement event. The right-hand side, the probability on the right-hand side is the complement of x being between 40 and 60, which is the absolute deviation from 50 to be greater than or equal to 10, or which, in other words, x is going to be at least 10 units distant from 50. And 50 is what? 50 is the mean of this distribution, right? So we can say that this probability cannot be known, maybe. However, according to the Chebyshev's inequality, the probability that a random variable to deviate from its mean at least 10 units is less than or equal to the variance of that random variable divided by the square of 10. And that is going to be 0.25. So that probability on the right-hand side is less than or equal to 0.25. If the complement event's probability is less than or equal to 0.25, then the original event here must be greater than or equal to, must have a probability that is greater than or equal to 0.75, right? So what I can say about this probability, basically, I cannot calculate that probability if I do not know the distribution functions. However, according to the Chebyshev's inequality, what I can say about this probability is it can never be less than 0.75. That probability can never be less than 0.75. So which means with 75 probability, the produced quantity can just be between 40 and 60.